shape and size of an antenna is a function of its purpose. But whatever its physical form, it is designed to transmit and receive electromagnetic waves. Let us first consider a hypothetical antenna, the point source. From such a source, energy radiates outwards in all directions. Let us examine this process more closely. The radiated energy can be represented by a traveling waveform of this shape. The waveform normally follows a sine curve. We will consider one complete cycle of the wave. It is defined as one wavelength. We can relate the wavelength of the radiation to the antenna which produced it. An antenna which accommodates half a wavelength is the simple dipole. If we feed a signal to this antenna, an electron flow will be set up within it. The electron flow first produces a maximum concentration in this direction, reverses, then produces a maximum in the opposite direction. Flow reverses, maximum. This cycle repeats itself at the signal frequency. This electron flow creates a fluctuating magnetic field. Let us relate the direction of this field to the electron flow. As the electron flow reverses, the magnetic field is at a maximum, and the lines of force are in this direction. When the flow stops, the lines of force collapse. As the flow reverses, the field again reaches a maximum. The lines of force are now in the opposite direction. The magnetic field thus reverses its direction at each half cycle of the signal frequency. This is known as the H field. The strength of this field is proportional to the amplitude of the current standing wave. This current standing wave is 90 degrees out of phase with the voltage standing wave. At this instant, the antenna has a positive voltage at this end and a negative voltage at this end. When the voltage builds in the opposite direction, the polarity reverses. This changing polarity produces an electric field in phase with it. When the voltage is of this polarity, the field is in this direction. When the polarity reverses, the field builds to a maximum in the opposite direction. This is known as the E field. The E and the H fields thus build and collapse 90 degrees out of phase with each other and constitute the antenna's immediate field. This immediate field produces the radiating wave pattern. From the antenna, we can visualize the radiation as a series of grids propagating outwards. The vertical lines are the H component, and the horizontal lines the E component. Notice that the lines are at right angles to each other, that is, in space quadrature. Vectorially, these lines represent the peaks of the radiating waves. Notice that their direction reverses at the next half cycle. Since the peaks of these two waves occur simultaneously, they are in time phase. The traveling waves are therefore said to be in time phase and space quadrature. The polarity of an antenna is determined by the plane of the E field. To obtain a maximum signal, both the transmitting and receiving antennas must be in the plane of the E field. The direction in which the E and the H wave pattern propagates is determined by a simple rule. To apply this rule, we use any two vectors. Imagine a corkscrew action. If we turn from the E vector to the H vector through the shortest distance, the screw has advanced in the direction of propagation. This is known as Poynting's vector rule. In the next half cycle, the E and H vectors reverse. Applying Poynting's rule again, we see that the direction of propagation is unchanged. Although we have considered only peak vectors, any vector pair would give the same direction of propagation. Let us now consider what happens when the wave strikes a reflecting surface. We will consider only one pair of the peak vectors. As before, Poynting's rule gives the direction of propagation. On reaching the reflector, the E field is reversed, but the direction of the H field is unchanged. By Poynting's rule, the direction vector is therefore reversed. The same process occurs for each successive pair of vectors. The direction of propagation thus reverses when the wave strikes a plane surface. Let us now see how we record the intensity of the energy radiating from an antenna. First, we sample the signal strength at various points. Such a record is geographical, and we can join the points of equal intensity to obtain contour lines. It is often more useful to know the shape of the field radiated by the antenna. To achieve this, we obtain field strengths at a fixed radius from the antenna. We now use a vectorial presentation to give each reading a magnitude and direction. To plot this, we use a scale of circles. Along this line, the field strength on the selected radius is 3. So we cut the line at the circle representing strength 3. Along this line, the field strength is 4. So it is cut at the strength 4 circle. By continuing the plot in this way, we obtain a series of vectors. These vectors represent the strength and direction of the field. Joining the tips of the vectors, we obtain the antenna's polar diagram. The complete polar diagram is three-dimensional, and it enables us to visualize an antenna's radiating characteristics. Let us now review the basic elements of antenna propagation. A half-wave dipole, excited by a signal, will have an electron flow set up within it. This movement of electrons creates two fields. These fields, building and collapsing in time and space quadrature, form the antenna's immediate field. This immediate field produces the radiating wave pattern. We can represent this radiation by vectors. Associated with these vectors is the traveling wave pattern. The traveling wave is in time phase and space quadrature. The fundamental characteristics of this traveling wave and the means by which it was produced are the same for any antenna system.